Assalamu alaikum everyone. My name is Abdullah Haider, and today I will be discussing chapter 5 of the course Differential Equations and Linear Algebra. So from chapter 1, you may remember solving differential equations using substitution method, Bernoulli, exact, linear, and other types of problems like mixture problems, Newton's law of cooling, heating. So in chapter 5, we will not be applying those concepts, but we will be now solving second order differential general differential equations, and we have many cases, and hopefully inshallah I'll make it as easy as I can. So before we begin, رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي. So second order general differential equation is in the form a y double prime plus b y prime plus c y is equals to a function of f(x). So here these coefficients, these can be constant numbers, constants, or also functions. In chapter 5, we will only be looking at the constants. So for the functions, you usually use the Cauchy-Euler method. However, I believe this is not covered in the material for this semester and the last semester. I'm not sure about this semester, but for now, we will not be covering the Cauchy-Euler method, which is if the coefficients are functions. But for the sake of this video, we'll be considering constant numbers for this differential equation. And if I want to find the general solution of a second order differential equation, it will usually be in the form y of x is equals to c1 y1 plus c2 y2. Now later on I'll explain why we have two solutions. This is the first solution and this is the second solution. Later on I will explain why why we have two solutions, but it's important to know that y of x, the general solution is y of x is equals to c1 y1 plus c2 y2, and y1 or y2, they can be equals to e power rx, or they can be equals to x e power rx, and they can even be in terms of cosine x plus sine x. We will all discuss them right now. So the only thing you need to know for now is y of x equals to c1 y1 plus c2 y2, and y1 and y2 can take any of these values, and I'll discuss them more in detail. So linearly independent solutions. Linearly independent solutions means that you cannot write one solution in terms of the other solution using numbers only. So let's say I have a solution y1 is equals to e power x, and y2 is equals to e power x. These mean the same solution, but these are not independent solutions. These are not independent. Why? Because I can write this by doing y1 and multiplying by this by 1, which will still give me e power x. So this is a dependent solution, and we don't want dependent solutions in this chapter. So y1 is equals to e power x, and y2 is equals to x e power x. Now let's test this out. You cannot, as I said, these are only linearly independent if they cannot be multiplied by, if y1 cannot be multiplied by a number to get the second one. So no matter what number I multiply this by, I can, no matter what constant I multiply this to 2e power x, 3e power x, I'll never get this x over here. This x is present just to make the solution independent. And the Wronskian is always used to determine the independence and dependence of solutions. So if I have y1, y2, and y1 prime, and y2 prime. You need to know the Wronskian. You will need this later for the variation of parameters. This is the formula. Y1, this is a matrix essentially. So we have the Wronskian. This is equals to y1, y2, y1 prime, y2 prime. This is in a matrix. So if I want, so let's test this out, y1 and y2, to show you why they're independent. So you have e power x, x, e power x, and the derivative of e power x is e power x. The derivative of this is, you apply the product rule, u prime v plus uv prime. U prime v is e power x plus u v prime, which is still x e power x. So when you calculate the determinant of this Wronskian, you'll get e power x plus x e power x minus x e power x e power x. So when you do the subtraction of this, when you subtract these, you will get a determinant which is not is equals to 0. So when the determinant of it, when the determinant of the Wronskian is not equals to 0, this means independent solution. And if the determinant of the Wronskian is equals to 0, then you'll have a dependent solution. For now, you don't need to know this much in detail, but just to give you an overall idea of why we cannot have two exact same solutions, why we cannot have EX and EX. So that's why we have to put an X here to make the solution independent. And that is it for the linearly independent solutions. Now, linear homogeneous second order equations. So above we discussed the general format of the second order differential equation, which is ay double prime plus by prime plus cy is equals to f of x. Now we want to know what happens if we put a 0 here, which will be discussed right now. So whenever you have second order equation on the left side and you have a 0 on the right side, to solve this kind of equation, you need to convert this into an auxiliary equation. Auxiliary equation. And in the auxiliary equation, you consider y prime as r square, y double prime as r square, y prime as r, and y is whatever the coefficient is beside it. So whenever you are asked to find the homogeneous solution or equation, what we always do is we find the auxiliary equation, which is this equation in terms of r square and r and the coefficient. So if I am to write this, this would be r square plus 2r minus, now I said the number beside y will be the coefficient, so it is minus 8 here, it is equals to 0. So now we will solve this auxiliary equation. And if I use my calculator to solve it, I will get R1 is equals to 2 and R2 is equals to negative 4. So these are the solutions to the auxiliary equation. And as I discussed before, that the general solution, the general form of the solution, y of x, is equals to c1 y1 plus c2 y2. So you need to know that whenever we have, so these two, so these are basically roots. When we have distinct roots and when we have repeated roots, we take we take y1 as e power r1x and y2 is equals to e power r2x. Let's consider only distinct roots for now, which is so basically the roots right now are r1 is equals to 2 and r2 is equals to 4. These are distinct roots. So what we do is we take y1 is equals to e power r1x and y2 is equals to e power 2x. So now we can write y of x is equals to c1 e power r1x plus c2 e power r2x. Note that the rule for distinct roots and repeated roots and complex roots are not the same. So we'll go one by one. So as I said before, these are distinct roots. 2 and negative 4 are different. The general form is c1y1 plus c2y2. And for the distinct roots, we have y1 is equals to e power r1x and y2 is equals to e power r2x. So now we can write the values of r. Y of x is equals to c1 e power 2x plus c2 e power negative 4x. This is our answer. And one important thing to know is this answer is always the homogeneous solution. Whenever we get the auxiliary equation and we write it in the general form, this is always called the homogeneous solution. So so basically for now, I do not advise using y of x for now, but just to say that we're basically finding the homogeneous solutions to all of these equations, and it's better to write y of fh is equals to c1 e power 2x plus c2 e power minus 4x. This is our final answer for this question. Now, same thing, what we'll do is, same thing for this question, but we have a different case here. We convert this into an auxiliary equation, which is r squared minus 6r plus 9. As I said, y double prime will be considered r squared, y prime will be r, and the y self you only take the coefficient. You equate it to 0, and if you solve for r, you'll get r1 is equals to so you get a repeated root. R1 is equals to 3, and R2 is also equals to 3. So in the above question, we got 2 and 4, which are distinct roots. However, in this question, we have got repeated roots. 3 and 3 are repeated. So for repeated roots, we have the general form. For all differential equations, we have the general form y of x is equals to c1 y1 plus c2 y2. So for repeated roots, we take y1 is equals to e power r1x, but y2 will now be x e power r2x, always. Why? Because we cannot have e power 3x plus e power 3x. That will not be, we cannot have y is equals to e power 3x plus e power 3x. This solution is dependent, as I said before. And if you do the Röntgen and you find the determinant of the Röntgen, this will be equals to 0, which is not what we want. We want the solution to be independent. And to make this independent, the solution independent, this is the reason why we put an x beside e power r2x this time. So now our homogeneous solution will be c1 e power 3x plus, now we have to put an x. Why? As I said before, we cannot have e power 3x repeated twice. So it will be plus x e power 3x. That is our answer for for solving this homogeneous equation. So always remember that whenever you have repeated roots from the auxiliary equation, 3, 3, which is repeated, for the second solution, you always have to include an x over here. It's mandatory and it's not avoidable. So c1 e power 3x was our r1, and y2 will be our x e power r2x. This is very important. That's it for this question. And now we have an initial value problem. This is an initial value problem. Y0 is equals to 2 and y prime 0 is equals to 1. So first, we always find the auxiliary equation. The auxiliary equation for this will be r squared plus 2r with the y you always take the coefficient and equate it to 0. Now you find the roots. You find r1 and r2. So when you find the roots, you get minus 1 plus I, and you get r2 is equals to minus 1 minus I. So you can see that these two solutions are now complex roots. Complex roots. Why? Because they have a real number and an imaginary number. And for complex roots, you always have to remember that you will have a sine and a cosine in the answer always. So if so y1 is going to be e power ax cosine bx. I'll explain what a and b are in a minute. And y2 is equals to e power ax sine bx. So in this context, a is the real part and b is the imaginary part. So going back to the general form, the general form of the solution, y of x is equals to c1 y1 plus c2 y2. So our homogeneous solution is going to be c1 e power ax cosine bx. Now here, what are a and what is a and what is b? A is the real part, which is -1, and b will be the imaginary part. Now for the imaginary part, you don't care, you don't look at the signs. This is 1i, and this is -1i. You only take the positive number from this. So you take 1. Why? Because in both roots, the coefficient of I is 1, and we do not have to take the negative root because the positive root will cover the solution. So just remember that A is the real numbers, this and this one, and B will always be the positive coefficient of the I. So we have A -1, B equals to 1. So our y1 is going to be e power -x cosine x plus, now what is C2? E power minus x sine bx. Now b is 1, so sine x. This is our solution to the general, this is our solution to the homogeneous equation, y double prime plus 2y prime plus 2y is equals to 0. And now if the question asks you for a particular solution, you have to apply the initial conditions. So if I apply y0 is equals to 2 here, if I apply y0 is equals to 2, I will substitute 2 here and 0 in all of the places where the x is present. So 2 is equals to, we need C1. So basically what we need to find is C1 and C2 in this particular solution. C1 e power -0 cosine 0 plus C2 e power -0 sine 0. So 2 is equals to, now e power -0 is 1, and cosine 0 is also 1, so C1 times 1 times 1 will give us 1. 1 C1 plus now C2 e power 0 is 1, but sine 0 is 0, so C2 times 1 times 0, which is 0. So you have 2 is equals to C1. So this is your C1. Now, if you want to find C2, no, this is not a good, no, this is not a good color. If you want to find C2, you take the derivative of the homogeneous solution. It's much easier to find the C2 using the derivative of the homogeneous solution. So what I'll do is, first write the homogeneous solution. Y of h is equals to C1 e power negative x cosine x plus C2 e power negative x sine x. And let's say I want to factor out e power x from here to make it easy. E power negative x C1 cosine x plus C2 sine x. So when I take the derivative, y prime will be the product rule. So the product rule is u prime v plus u v prime. So the derivative of e power minus x is equals to, I'm explaining, what do you want? ما في marker أصلا. Next time won't disturb me. So y prime of h is the product rule, u prime v plus u v prime. So the derivative of e power negative x is negative e power minus x. You write this as is c1 cosine x plus c2 sine x plus now u v prime. What is v prime? C1 negative sine x plus C2 cosine x. So now when we substitute our second condition, y prime 0 is equal to 1. I put the 1 is equals to y, and I substitute 0 everywhere else. So negative e power negative 0, C1 cosine 0 plus C2 sine 0 plus e power negative 0, C1 negative sine 0 plus C2 cos 0. So this will give us 1 is equals to, this will become negative 1. Cos 0 is C1, sine 2 will be, sine 0 will be 0, plus e power minus 0 is 1. C1 times negative sine 0, this will be 0, plus C2 cos 0. C2 cos 0 means C2 times 1, which is C2. So this will give us 1 is equals to negative 1. Now we found C1 from here. C1 is 2 plus 1 times C2. So we have 1 is equals to negative 2 plus C2, and our C2 will be equals to 3. So now we can say that the particular solution, or the particular solution, I will write YP. No, we'll not write by P. We'll write y of x is equals to. Now C1 we got 2e power negative x cosine x plus C2, which we got is 3 sine x. No. 3 e power negative x sine x, and that is it. That is our particular solution for these initial values. So just to give a quick summary, if you have so first of all, you start with finding the auxiliary equation in terms of r, and whenever you get r distinct roots, your y1 and y2 will be having the same form, e power r1x and e power r2x. So just remember that the fastest thing is C1 e power rx plus C2 e power rx. So you have a 2 here, so e power 2x, negative 4 e power negative 4x. If you have repeated roots, r1 is equals to 3 and r2 equals to 3, then C1 will be C1 e power r3x. But you have to put an x here for the second repeated solution to maintain independence, as I said before. So remember, y1 is equals to r1x, and the second one, y2, will be x times e power rx. And if you have complex roots, you will always have y1 is equal to e power ax cosine bx, and y2 is equals to ax e power ax sine bx, where a is the real part and b is the imaginary part. So just remember that the homogeneous solution will be C1 e power minus a cosine b plus C2 e power minus a sine b. So you always have the cosine and sine there. There's not much difference between this and this. The only difference is that in complex roots, you only have a sine here and a cosine here. That's it. You will always have a cosine and sine in the homogeneous equation. So now we will solve method of undetermined coefficients. So in the questions above, we had a 0 on the right side, another 0 on the right side, and another 0 on the right side. So these are homogeneous second order equations. But what if we get something which is not 0 in this case? We have 3e power 2x, which is exponential. And in the later questions, we have a sign, and then we have a polynomial. So for this for the method of undetermined coefficients, you have 3 cases on the right hand side. Case 1 is exponential. Case 2 is trigonometric. And when I mean by trigonometric, sine or cosine. Or you can even have both in the right hand side, it doesn't matter. And we can have a polynomial. So here you have 3e power 2x, which is exponential, and for the next 3 questions, I'll explain how to tackle the exponential questions. So whenever you have to use the method of undetermined coefficients, the form of y of x is always the homogeneous solution plus the particular solution. The homogeneous solution is basically what we did above, which was making the equation equals to 0, writing the auxiliary equation in terms of r, finding R1 and R2, and then writing this in terms of the homogeneous equation problem. But now we will add onto it yp, which is caused by the exponential. So first of all, we always find the homogeneous solution, which is this equation equals to 0. And if we need to find the auxiliary equation, it will be r squared plus 5r plus 6 is equals to 0. And r1 will be -2. And r2 is equals to -3. Now, remembering the rules from above, you might notice that -2 and -3 are distinct roots, distinct real roots. So we will use YH is equals to C1 e power R1x plus C2 e power R2x. So in this case, our YH is going to be C1 e power -2x plus C2 e power -3x. This is our YH, our homogeneous solution to this equation. Now we need to find YP, which is the particular solution. And for the particular solution, if we have an exponential, if we have an exponential on the right side, we take a constant a, and we write beside it what we have here on the right side. So YP will be ae power 2x. Now, whether you multiply this by x or you multiply this by x squared depends on whether YH and YP are similar. So from so you have e power 2x here. You have a e power -3x, which is not e power 2x. You have an e power -2x, which is not the same as e power 2x. So we will not multiply this by any x. We will not multiply this by any x, and this will be our yp, a power 2x. So as I said before, you check YH with what you have on the right side. E power -2x is not the same as e power 2x. E power -3x is not the same as e power 2x. So you will not multiply this by any x or x squared. This we will always have this a for the yp, because this can be any constant. It can be -2, it can be 0, it can be 3. So this is the yp. And I think you might still be confused about why we have e power O2x, but hopefully this will be resolved in the following problems. So our final solution to this problem is going to be C1 e power -2x plus C2 C2 e power -3x plus ae power 2x. As I said before, for the method of undetermined coefficients, your final answer y of x is going to be YH plus YP. This was the YH part, and this is the YP part. Now you might have confusion about YP. You might still have confusion about YP, but I'll explain it further here. So you have 4e power -2x on the right side. This is not a homogeneous equation. So what we have to do is find homogeneous equation and the particular solution, because we have an exponential over here. So YH is going to be r squared plus 5r plus 6 equals to 0, which is the same as above. R1 is -2, and R2 is equals to -3. So now you write the homogeneous solution. Since these are distinct roots, -2 and -3 are different, we will have C1 e power -2x plus C2 e power -3x. This is our homogeneous solution to the problem. And now we need to determine yp. As I said before, you take the constant as is, because it cannot always be 4. It can be 3, it can be 2, it can be 0. We take this 4 as a constant a, and we write it the rest as is. Now, you always have to check for this important thing. So let's consider this f of x. Do we have a similar f of x in the homogeneous equation? Let's check this. E power 3x is not the same as e power 2x. E power -3x is not the same as e power -2x, so we're fine. But you have e power -2x in the homogeneous equation, which is equal to this. E power -2x is equals to e power -2x. So this is not what we want. This will cause the solution to become dependent. So we want an independent solution. So since e power -2x appears once over here, we will multiply this by x. We will multiply this by x because e power -2x appears in the homogeneous once. You look at f of x here and see how many times it is appearing. In the above part, you have 3 power 2x. Now e power 2x was nowhere in the homogeneous equation, so we keep it as is. 3 becomes a, and e power 2x remains as is. But here, you have e power -2x, which appears once in the homogeneous equation. So that is why we have to multiply this by x, which is ax e power -2x. This is our particular solution to the homogeneous solution. And if you want the final solution, it's going to be y of x is equals to yh plus yp. So remember that y of x is equals to yh plus yp. And our yh is c1 e power -2x plus c2 e power -3x plus ax e power -2x. This part is the homogeneous solution. This is particular solution. Now, this question. Same as before, we start off by finding yh and yp. So yh is basically the auxiliary equation equals to 0. We're finding yh right now. R squared plus 4r plus 4 is equals to 0. Your r is going to be r1 is -2 and r2 is equals to -2. Now you have -2 and -2, which is repeated. This is repeated. So as I discussed previously, our solution will be C1 e power -2x, but the second solution will be multiplied by x because they're repeated. So x C2 e power minus 2x. This is to ensure that the solution is independent and not independent, so the Rorschkin can be. So forget what I said. Just remember that if you have repeated, the second one will always be multiplied by x. This is our YH. Now, over to YP. This is your f of x. And for YP, we have, let's consider 5 to be A, and the rest is the same. AE power negative 2x. So now you need to check if f of x appears in YH or not, and how many times. So this is e power negative 2x, and you have an e power negative 2x here. You have an e power negative 2x here. So basically, the e power 2x in the f of x on the right side appears twice in the homogeneous equation. So for this reason, you will multiply this by x squared. That's it. Why? Because you cannot have dependent solution. You cannot have the same exponentials being in f of x and y of h. So that is, and since this is appearing twice, you have e power 2x here, e power negative 2x here, e power negative 2x here. So you multiply this by x squared. So your yp becomes ax squared e power negative 2x. And your final solution, y of x, is going to be yh plus yp. C1 e power negative 2x plus x C2 e power negative 2x plus yp, which is ax squared e power minus 2x. This is your YH, this is your YP, and that's it for the question. So a general summary, you have to solve a question using the method of undetermined coefficients whenever you don't have a zero on the right side. What you do is you find the homogeneous solution and the particular solution. Homogeneous solution is as before. You write this in terms of R and find the roots. And since these are distinct roots, you have C1 e power negative 2x plus C2 e power negative 3x. And to find YP, you take the constant here as it is, constant, but in terms of A. 3 becomes the A, and you take the exponential as is. And since e power 2x is not appearing anywhere over here, it's not appearing over here. It's not appearing over here, so we don't multiply this by x. Here we have an e power minus 2x on the right side. So as I said before, you find the homogeneous solution first. Make this in terms of R, solve for R, and these are again distinct roots. So you'll have C1 e power negative 2x and plus C2 e power negative 3x. This won't be multiplied by x because these are distinct. And you check if e power negative 2x is appearing in the homogeneous solution. So it appears once, which is over here. That is why you multiply yp by x. Yp is essentially a, and then the exponential over here. Why x here? Because the f of x here, which is e power minus 2x, is appearing once in the homogeneous solution. So multiply this by x, and it becomes ax e power negative 2y. E power negative 2x, and then you combine the solution yh and yp. Finally, this is a method of undetermined coefficients as well. There's no zero here. This is f of x. So find yh, which is the auxiliary equation, make it equals to 0. And since this is repeated, our homogeneous solution will be C1 e power negative 2x plus x. C2. Why x? Because this is repeated and you cannot have e power negative 2x twice. And then we assume that yp, you make this 5 become an a, and you keep the exponential same. But since e negative 2x is appearing twice, once here, so this will become x squared. You multiply this, becomes yp is equals to ex squared ex squared e power negative 2x, and then you add up yh and yp, and that's it. All right, so now since we have finished the all possible cases for exponential, we'll now move on to trigonometric. Now in trigonometric, on the right hand side of the differential equation, you have three possible cases: sine bx by itself, cosine bx by itself, or you can also have both of them together, sine bx plus cosine bx. So in this question, we only have sine. So as I said before, whenever we want to find the solution to the whole equation, y of x is going to be homogeneous solution plus the particular solution. Now, just a general note, whatever case you get on the right side, whether it's exponential, whether it's trigonometric or polynomial, you always and always have to find yh in the first place, and then your yp will be determined by whatever you have on the right hand side. So first I'll start by finding the homogeneous solution. R squared plus 4r is equals to 0. Oh no, mistake. If this is, I would have 4r if there was a y prime, but since we have a 4y, we always take coefficient of the y, which is 4. So we get r1 is equals to 2i, and r2 is equals to negative 2i. Now notice that these roots are complex. And before we discussed that if we have complex roots, our y1 is going to be e power ax cosine bx, and our y2 is going to be e power ax sine bx, where a is the real part and b is the imaginary part. So our yh is going to be e power ax, I forgot the c1, c1 e power ax cosine bx plus c2 e power ax sine bx. So now we substitute whatever we have for a. So basically our a is 0 here, and why? Because a is the real part and we don't have a real part in the roots. So a is 0 and b is the positive coefficient of the imaginary part, which is 2. So our homogeneous solution is going to be c1 e power, so e power 0 is going to be 1, e power 0x, which is e power 0 is equals to 1. So I can just skip writing e power 0 over there just to save time. C1 cosine 2x plus C2. Same here, e power 0x is going to be 1. So C2 sine 2x. Now so basically now we need to find yp. Whatever you get on the right side, whether it's sine bx, whether it's cosine bx, or whether both of them together, it will always be, your yp will always be a cosine bx plus C sine bx. Now, one important thing to note is the small b and the big B are different. The big B is basically the coefficient of x what we have inside the sign. So our yp is a cosine 3x plus c sine 3x. Now, as I said before, and as we did in the last three cases, we need to check whether our homogeneous solution has anything common with sine 3x. So here we have a cosine 2x and we have a sine 2x. None of them are related. So cosine 2x is not the same as sine 3x. Sine 2x is not the same as sine 3x. So we don't have to multiply this by x. We will not multiply this by x. So this is our assumption for yp. So as I said before, whatever situation you get, whatever type of trigonometric function you get on the right side, whether it's sine, cosine, or both of them together, your yp will always be a cosine bx plus c sine 3s plus c sine bx. So, and this big B is what you have, is always what you have here. And we did not multiply this by x since it's not related to, since the function here is not related to homogeneous solution in any case. So that's it for this question. We found yh and yp, and you can simply just find y of x by adding them up. Now this question. Here you will face a different scenario one. So let's see. So as I said before, y of x is equals to homogeneous solution plus particular solution. Here your homogeneous solution is going to be r squared minus 2r plus 5 is equals to 0. You have the roots. R1 is equals to 1 plus 2i, and R2 is equals to 1 minus 2i. So once again, you have complex roots, and our homogeneous solution will therefore be in the form C1 e power ax cosine bx plus C2 e power ax sine bx. Hence, our final homogeneous solution is going to be C1. Now we have a real part here, so a is equals to 1. B is going to be the positive coefficient of the imaginary part, which is 2. So C1 e power x cosine 2x plus C2 e power x sine 2x. This is our homogeneous solution. And now we will find the particular solution. So we have a sine 2x here, which means we can make the assumption a cosine big Bx plus c sine big Bx. Now, your yp, so our big B is 2, a cosine 2x plus c sine 2x. Now, before moving on, you check whether your homogeneous solution has something in common with the f of x here. Just like how we did for the exponential part. Once you find the homogeneous solution, you check if something is common. Like let's say we had e power negative 2x here, and in the homogeneous solution we have e power negative 2x, so we have to multiply the yp by x, and we have e power negative 2x in the f of x here, and we have it twice in the homogeneous solution, so we'll multiply this by x squared. So it's the same principle over here as well. You have both sine 2x in the homogeneous solution and sine 2x in the homogeneous solution. So now you compare. You compare if there's something in common. Cosine 2x and sine 2x are not the same, but sine 2x over here is the same as sine 2x here. So therefore, our final yp is going to be this multiplied by x. That's it. So if you want to expand further, ax cosine 2x plus cx sine 2x. Once again, why did we multiply yp by x? You look at the homogeneous solution and see if one or more functions here have something in common with the function on the right hand side. So you compare cosine 2x with sine 2x, which is not the same, but you have sine 2x here and sine 2x here, so you multiply the whole thing by x, and that is your final yp. And so your final y of x is going to be this y of h here plus y of p. So you add them up. Let me add them up, by the way. So your y of x is going to be c1 e power x cosine 2x plus c2 e power x sine 2x plus what we have here, ax cosine 2x plus cx sine 2x. This is your yh, this is your yp. So that's it for the trigonometric. And you will so basically in these kind of questions you always have to pay attention to whether there's something common in yh and the function here, so that you can know whether you multiply a yp by x or not. This is something you should really remember and focus on. So finally, we're into the last type of the method of undetermined coefficients, where you have a polynomial on the right hand side. So you have a polynomial on the right hand side. And I will be giving just a quick note on the cases. So basically we will start off by finding our homogeneous solution. But when we find R1 and R2 and we get R1 and R2 are not equal, so both of them are not equal to 0. So your yp will remain same. If either one of, if R1 is equal to 0 and R2 not equal to 0, or if you have R1 is not equal to 0, or R2 is 0, basically one of them is 0. So your yp will be multiplied by x. And if both of them are 0, if R1 and R2 are equals to 0, then your yp will be multiplied by x squared. So we'll see them now in these cases. This is a polynomial on the right side, so you will find y of x, which is yh plus yp. So so the yp for all polynomial functions is equals to the what do we call it? The highest degree polynomial. I might not sound right, like you might not understand what I'm saying, but if you have x squared on the right side, then this means you will have ax squared plus bx plus c. If you have x on the right side, then your yp is going to be ax plus b. If you have a constant on the right side, means you don't have any polynomial. Like you have a polynomial, but there's no x. You have a constant number. Then you'll only take a. And if you have an x cube, then it's going to be ax power 3 plus bx power 2 plus cx plus d. So you basically get my general idea. Your yp is going to be the highest order expression of that polynomial. So first we find the homogeneous solution, and I'll be quick this time. I have a quiz right now. So yh r square is equals to 0. R square, why? Because we have y double prime. Or oh yeah, we have a y. So r square plus 1 is equals to 0. And yeah, r1 is equals to I, and r2 is equals to negative I. So your homogeneous solution is going to be, so this is complex, this is the complex root. Your a is equals to b, 0, and b is equals to 1. So quickly, c1 e power 0 is going to be 1. E power 0 is equals to 1 multiplied by uh, cosine x plus c2 sine x. So this is your homogeneous solution. And as I said, yp is going to be the highest degree polynomial of the f of x on the right side. So ax squared plus bx plus c. Now we won't multiply, no, so this is our yp only, and we won't multiply by x because none of the r's are equals to 0. So as I said, if r1 and r2 are not equals to 0, yp will remain as is. And we will see r1 is equals to 0 in this next case. So same idea. Homogeneous solution r squared plus r is equals to 0. Here r1 is equals to negative 1 and r2 is equals to 0. These are distinct roots. So your homogeneous solution is going to be c1 e power minus x plus C2 e power minus 0. So e power 0 is going to be 1, so C2. Now, so this is your the homogeneous solution. So this is our YH, and as I said, your YP is going to be the highest degree polynomial expression of f of x here. So we have x squared, which we can write as ax squared plus bx plus c. Now, we check our R1 and R2. We have R2 is equals to 0, which means, as I stated here, if R2 is going to be 0, basically one of the R's is going to be 0, then you multiply YP by x. So you multiply YP by x, and then the final solution is that you add them up. So the last case, y of x is equals to homogeneous solution. That's the particular solution. So here, the homogeneous solution, r squared is equals to 0, r1 is equals to 0, and r2 is equals to 0. So both of them are 0. Homogeneous solution is going to be C1 plus C2. Why there is no e power on that? Because it's e power 0, which is 1, so we don't have to write exponential here. So this is your y of h, and y of p is going to be the highest degree polynomial expression of the right side, which is ax squared plus bx plus c. Now we have both of them 0. And what I said here before, if you have both r1 and r2 equals to 0, then you multiply yp by x squared. So you multiply this whole thing by x squared. Then you get yp is equals to ax power 4 plus bx power 3 plus cx power 2. So this is the final particular solution, and if you want y of x, this is going to be c1 plus c2 plus ax power 4 plus bx power 3 plus cx power 2. This is the final answer. So now that we have covered all the cases and examples of methods of coefficients with different types of functions on the right side, like exponential, trigonometric, and polynomial, now we'll be testing our knowledge based on these two past quiz questions. I got this question in my quiz, and we will be solving this. So we are asked to solve this initial value problem, and this is the first time I will show you how to solve the initial value problem itself. What I was doing in the cases was I was just finding the homogeneous solution and YP, but now we will learn how to find the constants as well, A, B, C, and all that. So consider this like an actual question which you could get in an exam. So what we want to find is y of x is equals to yh plus yp. So our yh is going to be r squared minus, why am I writing y? Minus 4r plus 4 is equals to 0. And here r1 is equals to 2, negative 2, by the way. And r2 is equals to negative 2. So these are repeated roots. So your homogeneous solution y of h should be equals to c1 e power minus 2x plus c2. Now, since this is repeated, we should multiply this by x, e power minus 2x. So, first of all, as always, we find the homogeneous solution to this equation. So we have this auxiliary equation r squared minus 4r plus 4. R1 is so these are repeated roots and distinct real roots. So we have c1 y1 plus c2 y2, and y1 is e power rx, e power r1x, and e power r2x. So we have c1 e power minus 2x, and since this is repeated, we have an x over here. So this is our homogeneous solution. Now, this is the first time you will be noticing that you have a polynomial and you have an exponential at this at the right side, both at the same time. So you don't have to worry anything about this. You go to yp is equals to. Now, what did we say that the yp for the polynomial will be? The highest degree polynomial expression. So you have an x over here, means the expression should be ax plus b, and the exponent you should so this is basically the part the yp for 4x, and for this one we'll have c e power rx. I cannot repeat a again, so c e power rx, and since our r here is 1, so we can simply put 1 here. So c e power x, basically the same thing. So this is so basically this is the yp for the polynomial ax plus b, and we have an exponent, so it should be a constant multiplied by the same exponent. And now, till now in the previous examples, this is what we have done. We have just identified YH and YP. But now the initial value problem is asking us to find C1, C2, AX. We need to find A, I need to find B, and we also need to find C. So we will basically we will take the first derivative and the second derivative of yp and substitute it in this equation, and then match the coefficients. So if I take the first derivative of yp, you will have a plus ce power x. And then if I take the double derivative of yp, this will be ce power x. Okay. And as I forgot to mention, you should always check if YH and YP have something, YH and the function have something in common. So you have e power minus 2x, and you have x e power minus 2x. So basically, there's nothing in common, so you don't have to multiply anything in YP by x, so you're perfectly good to go. So now we will substitute this y double prime, y prime, and yp in this equation, and then compare to the right side. So you have y double prime, which is ce power x minus 4. This will be a plus c e power x plus, and then 4y, our original equation, our original yp, ax plus b plus ce power x, and we equate this to what we have on the right side. 4x plus e power x. So now we expand. We get ce power x minus 4a minus 4c e power x. Trust me, this question is kind of long, and the next question will be even longer than this. 4ax plus 4b plus 4c e power x is equals to 4x plus e power x. Now, what we do is we group them. You combine the CE power x, you combine the CE power x, you combine the CE power x so that you can get so that you can compare to its e power x here. And so this is basically a polynomial. This is a polynomial, this is a polynomial. So you compare it with this. So you add up all the like terms. So now I will get, so I'm focusing on the exponent first. CE power x minus 4CE power x plus 4CE power x, and then you equate this to e power x. So minus 4 plus 4 cancel out. CE power x is equals to e power x. So your C will be 1. So this is your C. And now we want to find our A and B. So this is our C, we have got 1. So now we combine the polynomial terms. Minus 4a plus 4ax plus 4b is equals to 4x. Did I make a mistake or something? Minus 4a plus 4ax plus 4b is equals to 4x. Ah, okay. So when we get to this step as well, we compare this and this. Why? Because we have 4ax. So we'll compare this 4x. And since there is no constant on the right side, we will equate 4a and 4b to 0. Why? Because we have, so basically we have 4x, and but there's nothing after this, so let's consider there's a 0 here. So you merge the constants with the constants, you merge the x with the x. So after this, you'll get 4ax is equals to 4x, and then you'll get your a is also 1. And then since we have nothing after, so since we have nothing apart from 4x, we'll assume that we have a 0 here, and we'll do minus 4a plus 4b is equals to 0. So we already got a equals to 1 from here, so minus 4 plus 4b is equals to 0. A is equals to 1. So we have got it. So we've got our A, B, and C. So now we can say that our YP is equals to, now we can write this in terms of actual real numbers, x plus 1 plus e power x. So this is our YP. This is our final YP. This was our final our homogeneous solution. And now we will add both of them up to get y of x, and then we'll apply the initial conditions on y of x. So our y of x is equals to homogeneous solution plus yp. C1 e power minus 2x plus C2 x e power minus 2x plus x plus 1 plus e power x. These first two terms are yh, and these three terms are your yp. So important thing to know is when you're substituting this unknown yp in the main equation, you're supposed to get a, b, and c. You're supposed to get so basically the purpose of the initial conditions right now is to get C1 and C2. So we have y0 is equals to 2. So 2 is equals to C1. Now if I substitute 0 here, this will be 1 plus this will automatically become 0 because there's an s multiplied by x plus 0 again plus 1 plus 1 again. E power 0 is equals to 1. So you will end up with 2 is equals to C1 plus 2. Basically, your C1 is 0. This is your C1. Now, you will take the derivative. You will now take the derivative of y of x to be able to get C2. So if I take the derivative of this, well, there's actually no need to take the derivative for the first term because C1 is 0. So you can cross this out. So y prime will be now, assume we're using the product rule for this. This is u, this is v, then u prime v, c2 e power minus 2x plus u v prime, c2x minus 2 e power minus 2x, and derivative of x is 1, derivative of 1 is 0, and derivative of e power x is e power x. So the purpose of the derivative is to find C2. So now we have found the derivative. We will apply this initial condition. Y prime 0 is equal to 2. So we have 2 here, and substitute 0 everywhere. If I substitute 0 here, I'll get e power 0 just 1, so C2 is by itself. Plus, if I substitute 0 here, if I substitute 0 here, this whole thing becomes 0. Plus 1. If I substitute 0 here, this will become 1. So 2 is equals to C2 plus 2. And once again, C2 is equals to 0. So in the end, our y of x, what is our final answer to this? It's going to be, so C1 is 0. We've canceled out this term. Now C2 is also 0, so we'll cancel out this 2. So these two are cancelled because C1 and C2 are 0. So this will be our remaining terms. So in the end, after applying all initial conditions, our final answer is x plus 1 plus e power x. Now I understand this is long and the first time I'm applying the initial conditions, but basically the purpose of all this was to give you an idea of how to handle every single case, and the initial value problems are just an application of what we did before, but this time we're applying all the conditions, we're finding all the constants. So a quick summary, we have to find y of x, which is homogeneous plus particular. You first make the auxiliary equation equals to 0, find the roots, and since this was a repeated root, This is so this is a real the answer is repeated real roots. So our homogeneous solution will be C1 e power minus 2x plus 2 C2. Multiply this by x because this is repeated, then e power minus 2x. Then, as I said, the next thing you have to do is to find yp and yp. So don't panic if you have polynomial exponential together. You can have polynomial trigonometric together. You can have exponential trigonometric together. It depends on which professor will give what question, but you can so basically the thing is you can put them in the same equation. For polynomial, we said you look at the highest degree, which is x, and you write the expression for it, which is ax plus b. Then for exponential, you have a constant multiplied by whatever, the constant multiplied by the exponential itself. So we found yp, and that is what we used to do until this is what basically we used to stop here in the past examples. But since this is an initial value problem, we have to find a, b, c. We have to find c1 and c2. So to find a, b, and c, you take the first derivative and the second derivative, and then you substitute into the main equation. You substitute y double prime, y prime, and y into the main equation, expand, then, as I said, you equate the exponents with the exponents together. You equate the polynomial with the polynomial together, and when you reach the polynomial, part, you equate the x with the x, and since there was no number, there was not another number, so you assume that this is 0. You do 4a minus 4a plus 4b equals to 0. You find a, b, and c. You will get your proper particular solution. And the next part is to add up the homogeneous and the particular into one equation. So this was the part. This was our homogeneous. This was our particular, and then to find C1, you apply the initial condition. You get 0, and then you can cross this out. But to find, remember that the second initial condition is always used to find C2, and you have to take the first derivative of the main equation. And after you apply the initial conditions, you'll get C2 as well. And then you apply C1, C2 in the main equation, and that will be your final answer. So C1 was 0. This whole thing is gone. C2 was 0. This whole thing is not gone. So you're basically left with this x plus 1 plus e power x. Now, if you get such numbers, if you feel like you're getting zeros, ones, if you're getting like real actual whole numbers, when I was doing this quiz, I got C1 equals to 0 and C2 equals to 0, but I was confused, like why am I getting this 0? I was being so confused, and I was not able to complete the question. I lost half of the marks for that question because I was feeling confused. Like why is C1 0, C2 0? You cannot be. I did all these previous examples myself, and I never encountered this situation. But then later it turned out that you can have such numbers. Basically, otherwise you can tell me if I got C1 0, C2 0, then what was the purpose of doing all this? What was the purpose of finding? What was the purpose of applying the initial conditions when YP was already given and that turned out to be the final answer? But it depends on the numbers of the question. Miraculously, you got C1 0, C2 0. There's nothing we can do about it. So if you feel you're getting irregular numbers in your quiz, like zeros, which canceling out the answer, don't worry about this. Maybe it's something valid. So that is my take on this question. And the purpose I'm teaching you this is so that you don't face the same situation as I did before. All right, so we will be attempting this question. You have y double prime minus 3y prime plus 2y is equals to 3e power minus x minus 10 cosine 3x. Note that you have an exponential over here. You have a trigonometric over here. And as always, the way to start is find the homogeneous, then make an assumption for yp, and then find constants. So let's first find the homogeneous solution, yh. So this will become r squared minus 3r plus 2 is equals to 0. So your r values will be 1, r1 is equals to 2, and r2 is equals to 1. Note that these solutions are distinct, hence our solution for the homogeneous will be C1 e power 2x plus C2 e power x. Just let me confirm. Yeah. So R1 is 2, R2 is equals to 1, distinct. So our homogeneous solution will have C1 Y1, where Y1 can be e power R1x, Y2 can be e power R2x. So after substituting the R, this is what you get. This is your homogeneous solution. And now you will make an assumption for YP. So we have an exponential. Always we have a constant outside, and we take the exponential as is. So this is the assumption we have made for exponential, as I've discussed before. You take a constant and take the exponential as it is. Plus, now we have a cosine over here. Forget the minus sign. You should not look at the minus sign when deciding on the YP. So you have a cosine, and as I said before, if you have a sine or cosine and sine plus cosine together, it always has to be b cosine 3x plus c sine 3x. This is your YP. Whenever you have a cosine, sine, or sine plus cosine together, always take cosine and sine as it is, and put the constants b and c. And first, better to check whether we have to multiply our YP by x or not. C1, so we have e power 2x, which is not here, so that's fine. We have e power x, which is not here, so that's fine. So this is our YP. And in all of the examples we have done till now, before the question above this, we had only stopped until YP. However, this is an initial value problem. So we need to find the values of C1, C2, A, B, and C. So that is how will we get A, B, and C? We take the first derivative and the second derivative, then you put it in this equation. Substitute in this equation and equate it to the right side. So y prime of p will be minus a e power minus x minus 3b sine 3x minus 3x plus 3c minus 3c, no, plus 3c cosine 3x. This is your y prime, and then your y double prime of p will be a e power minus x minus 9b cosine 3x minus 9 minus 9c sine 3x. So this is your y prime p and y double prime p. Now we can substitute in the main equation to find constants a, b, and c. So we'll keep y prime as it is, y double prime as it is. A power minus x minus 9b cosine 3x minus 9c sine 3x. This is our y double prime. Now, if to avoid mess and congestion all over here, I'll multiply by negative 3 over here so that you can have something really like neat and tidy. So when you multiply so you have minus 3y prime. You multiply y prime p by negative 3, so you get plus 3a e power minus x plus 9b sine 3x minus 9c cosine 3x. This is your minus 3y prime plus, now we have 2y. So we multiply our yp by 2. Multiply this by 2. So you get 2a e power minus x plus 2b cosine 3x plus 2c sine 3x. All of the above is equals to 3e power minus x minus 10 cosine 3x. Now we equate the same terms. So we have 3e power negative x. We can add this. We can add this. We can add this. Equate it with this. A so when you add these up, 1 plus 3 4 4 plus 2 6. So you get 6 a e power minus x is equals to 3 e power minus x, and you get a is equals to 1 over 2. This is our a. Now to find b and c, first of all, you have a cosine here. You don't have a sign here. You don't have a sign here, so assume that we have a plus 0. And then equate sine. So equate cosine to cosine and sine to 0. So we're looking at the cosine now. You have cosine here, cosine here, cosine here, and cosine here. So now I'll do. You will actually get a system of equations for b and c. So minus 9b cosine 3x minus 9c cosine 3x plus 2b cosine 3x is equals to negative 10 cosine 3x. So when you equate this, you'll get negative 7b minus 9c minus 7b cosine 3x minus 9 cosine 3x is equals to negative 10 cosine 3x. So you can factor out minus cosine 3x from both sides. Minus cosine 3x, factor them out, you'll get 7b plus 9c is equals to 10 negative cosine 3x. You can cancel this out, cancel the cosine. So you're left with your first linear system of equation, 7b plus 9c is equals to 10. This is your first linear system of equation. So we're done with the cosine, and now we have to equate our sines. So we have a sine here, we have a sine here, we have a sine here. So this will give minus 9c plus 2c. Minus 9c plus 2c will give you minus 7c sine 3x. However, minus 7c, you add minus 9c plus 2c, which is not minus 7c, plus 9b sine 3x plus 9b sine 3x. And since you don't have a sign on the right hand side of the equation, you assume that we have a 0, and you equate the sign to 0. So when you factor out sine 3x, you're left with minus 7c plus 9b is equals to 0. Divide both sides by sine 3x, you get minus 7c plus 9b is equals to 0. So we have our second linear system of equations. Minus, better to write it like this, 9b minus 7c is equals to 0. Now you can I'll use my calculator to find b and c quickly. But note that in the exam, you have to show your work by substitution or elimination, whatever you like. So you get b is equals to 7 over 13, and your c is 9 over 13. So yeah, now you have a, you have b, you have c. You can finally get a proper YP equation. You can finally write the proper YP equation. So you have your YP is equals to e power minus x. A is 1 over half, so 1 over 2. 1 over 2 e power minus x. Then b cosine 3x. 7 over 13 cosine 3x. Then you have c sine 3x plus 9 over 13 sine 3x. This is your YP. Now, if you want to write your whole y of x, you want to write your whole y of x is the homogeneous solution plus YP. So the homogeneous solution was C1 e power 2x plus C2 e power x plus half e power minus x plus 7 over 13 2 sine 3x plus 9 over 13 sine 3x. This is your whole equation. The first two terms are your homogeneous, and your last three terms are the particular. Now, since this is an initial value problem, we have to substitute y0 is equals to 1. Y0 is equals to 1. So 1 is equals to, when you substitute 0 here, this becomes 1. This becomes a 1. This becomes a 1. This also becomes a 1. This becomes a 0. So we have C1 plus C2 plus half plus 7 over 13 plus 0. So your C1 plus C2 should end up being negative 1 over 26. Once again, this is your first linear system of equation. And now, if you want to find C1 and C2, you need to take the derivative of your y of x and then apply this initial condition. Y prime 0 is equals to 6 to 2. So when we take our y prime of x, you get 2c1 e power 2x plus c2 e power x minus half e power minus x plus negative 21 over 13 sine 3x plus 27 over 13 cos 3x. So now you can substitute your initial condition, which is y prime 0 is equals to 2. So you have 2 is equals to, now if I substitute a 0 here, this become a 1. 1, 1, this becomes 0. This becomes 1. So 2 is equals to 2c1 plus c2 minus half so this is already a 0 plus 27 over 13. So you should get now 2c1 plus c2 is equals to 11 over 26. This is your equation number 2. 2c1 plus c2 is equals to 11 over 26. Now you can find c1 and c2 again using substitution or elimination method. So you get your c1 6 over 13 and your C2 will be equals to negative half. So finally, you can write your final answer since you have all the constants now. So y of x is equals to C1 is 6 over 13 e power 2x plus, I think it's not a plus, it be a minus. C2 e power x. C2 is minus half, so minus half e power x. And you write the yp as it is. One over 2 e power minus x plus 7 over 13 equals 3x. Plus 9 over 13 sine 3x. And this whole thing is your answer for this question. Let me check if I'm right. This is really long. And so let's see. Correct, 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 correct. So this is our final solution. Quick summary. You have this differential equation, exponential trigonometric. You first find the homogeneous solution. Distinct roots apply as it is C1 y1 plus C2 y2. Then you find then for yp you assume a constant a, take the exponential as it is, and we have a cosine, so it'll be a cosine, a plus sign, and the constants b and c. Take the derivative, take the first derivative and the second derivative, then substitute into the main equation, and then equate the same terms. You'll get your a, b, and c, and then once you get your yp, add it to the main equation of y of x, then use the initial conditions to find your C1 and C2. All right, so now we'll move on to the last concept of chapter 5, which is the application in the mass spring system. So in the mass spring system, you have a block of mass m. It's on a horizontal surface, and there are walls or something, and then you have some springs attached to it. Okay, and the spring has a spring constant K. And if even though you might have taken university physics 1 or 2, this might be something new to you, which is the damping constant. Damping constant is denoted by C. So this is basically a kind of force which like hinders or stops the motion of the block from equilibrium. So like basically when you give the block a push to the right, let's say, or to the left, then the damping constant is basically damping is like a type of thing which reduces the energy of the system as it oscillates left and forth. So we assume that this is the origin, like the equilibrium position, and then once when you give it a push to the right, it will have an amplitude, let's say A, and if there is no damping, means energy is not being lost. So basically, this mass will be oscillating left right with the same amplitude and some speed. So basically, you will be in some questions you will be given something like you need to find the equation of motion. You'll be given a word problem. You find the equation from that first. You need to know how to find the period, time lag, time varying amplitude, determine whether it's critically damping or is there any damping at all. So we'll address that in a while. So the first thing I want to do is this question to start off with something simple. So in here, you consider the mass spring system whose motion is governed by the initial value problem. Now, first thing to note is all mass spring system questions for this chapter, you need to know this formula. mx double prime plus cx prime plus kx is equals to an external force if there is any. If there is no external force, in this right side will be zero. It will be equals to 0. So m here is the mass. This is the damping constant, and this is the spring constant. The spring constant. And this C is the damping constant, and this can be the external force if any. Okay, so it's like an extension of what we covered before, like when we solved question with y double prime, y prime, and y, and then sometimes it will be equals to 0, sometimes it will be equals to cosine x or polynomial trigonometric. Same idea. This is just an application of the mass spring system. So part A of this question is asking us to determine the position of the mass at time t. So basically, what is this? So basically, how we used to do in the previous concepts, that we were given an equation like this, and we had to find y of x. So basically, here you can just say that you're trying to find your y of x, but this time in the form of x and t. Basically, you have this 0 here. This is a homogeneous equation, so which means that you only have to find the auxiliary equation and then write your x of t. So first, the auxiliary equation for this will be r squared plus 4r plus 5 is equals to 0. And r1 will be minus 2 plus I. And r2 will be equals to minus 2 minus I. Now, we used to write y of h first, but since we are given the equation in terms of x and t, we will write x of t. If there's something on the right side, if this is not a homogeneous equation, then we would first write x of h. But since this is already a homogeneous equation, we don't have to worry about x of h. You don't have to write x of h like literally. So this would give us C1. Note that A is equals to -2. B is equals to positive coefficient of I, which is 1. C1 e power minus 2t cosine t. This B is 1 plus C2 e power minus 2t sine t. This is your x of t, but we're not done yet. we are not done. They gave us initial conditions for a reason. Because this is an initial value problem, you cannot just stop here and move on to part B. You cannot even solve part B without finding C1 and C2. So now, using this initial conditions, you need to find C1 and C2. So if you substitute 0 here and then substitute 0 everywhere else, C1, this will give you 1, cosine 0 is 1, plus C2, 1, sine 0 is 0. So 0 is equals to C1. This is your C1, 0. So you can just do x of t. Better, by the way, better to get rid of, since we have to find the x prime first, it's better to get rid of this part since d equals to C1 equals to 0, you can just literally like get rid of this part. So what you have left is C2 e power minus 2t sine t. Now we can find the derivative. X prime of t is equals to, now note that you need to use the product rule here. Assume this is u, this is v, u prime v plus ub, u prime v plus ub prime. So this will give you minus 2c2 e power minus 2t u prime v plus u cosine t. Now you can apply the initial condition. X prime 0 is equals to negative 3. Negative 3 is equals to, now minus 2 c2, this will give you 1, 0, sine 0 is 0, plus c2, putting 0 here is 1, cosine 0 is 1. So you get minus 3. Now the whole thing is 0 plus C2. So this is your C2. Finally, you can write your y of x. Your x of, your x of t. I'm used to these mistakes. So x of t is minus 3 e power minus 2t sine t. This is your x of t. Final answer for x of t. Now, determine the first time when the mass passes through the equilibrium position. The first time. So let's assume that the mass was already stationary. Let's assume that at time is equals to 0, and its position was position. So let's say this was the origin. This was the origin O at t equals to 0, x is equals to 1. So we need our new time for which the x would be 0. So let's say t1 was 0. We need to know our second time when x will be 0, because according to this differential equation, it will either move right or left, and after moving right left, it will come back to the equilibrium position here. So we need the second time. We need the second time it will come back to the origin. So at equilibrium position, x will always be 0. Basically, your x of t will always be 0. So now you can substitute 0 in this equation. 0 is equals to negative 3 e power minus 2t sine t. Now, what I advise you is not to, now if you don't know how to solve this equation, you don't have to go to the calculator, by the way, for this question as well. This part can never be 0. Why? Exponential is always positive. If you draw the graph of exponential, if you draw the graph of exponential, it's always like this. and going up like this. It basically never touches 0, which means that you cannot use this expression to solve to find the value of t, basically because the exponential approaches 0 from the left. If you if you try to go back and back in this graph, it'll approach 0 but never touch it. So you cannot use exponential to solve this equation, because this can never be 0. But you do know that the sign can be 0. So hence we'll make our sine t is equals to 0 now. Sine t is equals to 0. So what we can do is we can draw a graph. I'm sure you know this from Calc 1 and Calc 2. A sine graph looks something like this. It has a period of 2 pi. This is 2 pi. This is pi. This is 0. This is 1, -1. So the sine graph looks something like this. So it was already at 0 in the beginning. Let's assume that this was your T1. Now, when does it become 0 again? Here. At x pi, let's say t is equals to pi, your x pi becomes 0. It's literally touching the x-axis. So your final answer for this question is determine the first time when the mass passes through the equilibrium position. Your answer is simply t is equals to pi. If the trigonometric expression is really not that straightforward, then you can use your calculator and then solve for x or t, however you like. But since this is just a simple, since this is just a simple equation, I showed you through the sine graph that at t is equals to pi. So basically, this was the initial position, and you need to know the time when it comes back to 0. So this is pi. Simply, this is your answer. And in seconds, t is equals to pi seconds. That's it for this question. And now we can move to the advanced one. So basically, the equation is the same as it was, as how we did it, but the initial conditions are different. So let's first find our x of t. We can use the same general equation from below. C1e power -2t cosine t, because the equation is same, but the initial conditions are different. So we'll use the new initial conditions for the first problem. So we got xt is equals to c1 e power -2t cosine t plus c2 e power -2t sine t. So we'll apply our new initial conditions for this problem now. x0 is equals to 2. So 2 is equals to c1. This will give you 1. This will give you 1. Plus c2 will give you 1, 0. 2 is equals to c1. This is your c1, which is 2. Now you found c1. To find c2, you can use the derivative and then apply this condition. What would be easier is to first factor out the e power 2t. So x of t is equals to e power -2t power 2t, and then you can substitute c1 now. 2 cosine t plus c2 sine t. It makes it easier because here you have to do the product rule twice, You have to do the product rule here. You have to do the product rule here. Here, I have to do it only once. Basically, this will be my u, and this will be my v. So when I do the derivative, x prime of t, u prime, which is 2e power minus 2t, 2 cosine t plus c2 sine t plus, you will stay the same, e power minus 2t, then you do the derivative for v minus 2 sine t plus c2 cosine t. Now you can substitute the initial condition, x0 is equals to 1. 1 is equals to, substitute 0 everywhere, minus 2, 1, and then 2, 1, plus 0, plus 1, 0, plus C2. So you end up with 1 is equals to 0 mistake. So I'm doing 2 minus 1. Okay. Two. U prime B. What is the mistake? U prime. Oh. This is minus 1. My bad. So, yeah, I forgot the C2, and now your C2 will be is equals to 3. So you have your C1 and C2, and you can finally write your x of t equation is equals to e power minus 2t, 2 cosine t, plus 3 sine t. This is your final equation in x of t. But here, they want to find the function x of t that describes the motion in the form, this one. They want in this form. Before I get to this, I'll explain a few some formulas you really need to know. So C is considered no, this is not the small c. This is not the damping constant. This is the big C. And this big C is called amplitude. 1 second. I think I should write this question here first. So the question is asking us in terms of x of t is equals to CE power, how was it again? Alpha t cos omega 1t cos omega 1t minus delta. Delta, right? Yeah. So this C over here is called the amplitude. And if you take the CE power alpha t itself, if you take the CE power alpha t as it is, this is called the time varying amplitude. It's pretty obvious because it is in the function of t. Basically, this will be changing as t changes, and c is basically like the amplitude or like the farthest distance it goes until it switches direction. And omega 1 or omega, it doesn't really matter. This is the angular frequency, and also called pseudo frequency. These two mean exactly the same thing, pseudo frequency. And this is called the time lag. And then some other important things you will need to know is the big T. You might know it from physics 2, physics 1. This is called the period, but in math 211, it can also be the pseudo period. Period or a pseudo period. And then some key formulas you need to know. Is omega is equals to radical k over m, and the big amplitude C, this big C is equals to the square of C1, so C1 squared, C1 squared plus C2 squared, and what else? This time lag is equals to alpha over omega. So now, an important keynote is that this alpha, for the sake of this question only, this alpha and this alpha are not the same. Only for the sake of this question, this alpha and this alpha is not the same. This alpha actually means the angle. I'll explain what it actually means. But this alpha is the angle. This is the time lag. This is the frequency or angular frequency. And your period t can also be calculated by 2 pi over omega. And I think this is all you need to know. So how to find the C? C is equals to, we use the formula C1 squared plus C2 squared. our C1 is 2. So C2 squared, 3 squared. This will give you radical 13. This is your amplitude. Now, your alpha is the same as the A in the complex root of the auxiliary equation. And then your omega 1 or omega is the same as B of the auxiliary equation. So if we go back to what we did here, our our A was equals to 2 and our B was equals to 1. Basically, you look at the complex root of the auxiliary equation. So what you see, so this alpha, for the sake of this question only, because I don't know why the question was designed that this will be alpha, because this alpha is clashing with the alpha of the angle over here. But for this question only, just know that this alpha is the same as A, the real part, and the omega will stay the same for all questions. But this alpha is the only problem. I would say that would confuse many people. The omega will always be the imaginary part of the complex root. So in the previous question we had A is equal to -2, B was equals to 1. So we have our omega. In this equation, the only thing we're left with the time lag. So the time lag, delta, is equals to alpha over omega. And as I said before, this alpha is the angle, not A. So how to find this alpha? Alpha, also known as the angle, is equals to tan inverse C2 over C1. To be honest, you really need to memorize these formulas. The angle one is also important. It came in the final. And also you need to know this, the sign convention for C1 and C2. Where it is. Yeah. So assume that you have, let's say you have C1 and C2 as your X and Y on a 2D plane. And your C1 is positive, your C2 is positive. I'll write it like this, by the way, it will look better. So you have these cases where you have positive C1 and C2. You will have a negative C1 and a positive C2. You'll have a negative C1, you'll have a negative C2, you'll have a positive C1, you'll have a negative C2. It's something you might have learned in physics 1, where the alpha will stay as it is here. And then if you have negative C1 and positive C2, you have to do pi minus alpha. And if your C1 and C2 are negative, you have to do pi plus alpha. And if you have C1 positive and negative C2, you have to do 2 pi minus alpha. Once again, I'm telling you that this is important to know. If you, let's say you just find this alpha and then continue on, you'll probably lose 1 mark. If you are not able to, if you're not able to like understand when to add pi, when to subtract from pi, when to subtract from 2 pi minus alpha. So you need to really need to look into the sign conventions of C1 and C2 in this problem. So, but luckily, our C1 and C2 are both negative, are both positive. So we can say alpha is equals to tan inverse. C2 was 3, C1 was 2, and this will give Okay, is equals to tan inverse. This will be 0.9827. Now, I would prefer to keep the answer in radians unless it is specified in the question. So then our time lag is 0.9827 over omega, which is 1, is equals to 0.9827. That is your final answer for the time lag. So now we have found everything we need to put in this equation. So our x of t is c, which is radical 13, e power minus alpha t, like this. Cosine omega was 1, t minus the time lag. So you have radical 13 e power minus 2t cosine 1t minus time lag, which is 0.9827. That is your final answer. We have solved for this part A. So we have found our delta. We need to find our pseudo period and the time varying altitude. So we need to find our period, which is 2 pi over omega. So 2 pi over 1 is 2 pi seconds. That is, now we have found the period or the pseudo period. It really doesn't matter. And we know we need to find our time varying amplitude. This is already straightforward. It should be CE power 18, CE power alpha t. So your time varying amplitude is equals to radical 13 e power negative 2c. That's it. That's it for part B. So we found the period, found the amplitude, and you also need to pay attention to this. I put 0.9827. You can round it to 0.983. Now the most important part, determine whether the motion is overdamped, critically damped, underdamped. I don't have space. So I'm going to delete this since I've explained how the system works. All right. So how to know if there's no damping, how to know if there's underdamping, critically damping, or overdamping. You have 4 cases. Let's go to your case 1, which is no damping. No damping means C is equals to 0. Basically, your damping constant is equals to 0. And then your case 2 is under damping. Under damping is when C squared is less than 4 km. Then you have, what is the next one? Yeah. Then you have overdamped. This is when C squared is equals to 4 km. And finally, the last case, critically damped. In this case, you'll have c squared is greater than 4km. All right. So we know that this was written in the form of mx double prime plus cx prime plus kx is equals to 0 in this question. So our m is equals to 1, our c is equals to 4, and our k is equals to 5. So we need to check our c squared, and we need to find our 4km. So c squared is 16, and our 4km, 4 times k 20, 20. Yeah. So c squared is less than 4km. 16 is less than 20. So for c squared, when we have c squared less than 4km, we know that the system is underdamped. So we'll just choose underdamped. So you need to know these cases. If c is 0, no damping. So if c is 0 means you don't even have this part in the equation. Overdamping if you have these two numbers equal, and critically damped if c squared is greater than 4km. So that's it for this question. All right. So now we'll move on to our next concept, which is product of functions. So for this question, you will always be asked to find the general form of a particular solution. So whenever you have products on the right side, like this is a polynomial, this is a trigonometric. So here, basically, you're having products. So what the question is asking for is YP only. So you don't have to worry about these kind of questions. There is no initial value problem you have to solve. You only have to find YH and YP. So I will tell you how to deal with the product in just a minute. So as I said before, you start off by finding the homogeneous solution and then the particular solution. So our homogeneous solution in this case is r squared plus 9 is equals to 0. R is equals to R1 is equals to 3i, and R2 is equals to negative 3i. Complex roots, you have A0, B is equals to 3, A0 because there's no real part, B because the positive coefficient of I is positive coefficient of I 3. So we'll have our homogeneous solution in this case C1 cosine, and by the way, since we have a t, we'll use t this time, not x, plus C2 sine 3t. This is the homogeneous solution. So now we need to find YP. Now your YP, you will first find the YP based on the preferred order. So what I mean by order is you have to take these like you have to take the first function to be considered for YP. What I mean by is I'll explain in just a minute. Trigonometric, poly, and then exponential. So what I mean by order is you will first find the YP for the trigonometric function. Then if you have a polynomial function along with it, then you'll find the order, you'll find the YP for this, and then you'll find the YP for this in the last case. So if I am to find the YP of trigonometric over here, which is sine 3t, I will make the assumption A cosine 3t plus B cosine 3t. This is the YP for our sine 3t here. You always have constants a and b, and then you take this will be sine 3ct, by the way. I made a mistake. So whenever you have any trigonometric sine, cosine, or sine plus cosine together, your YP will always be cosine plus sine as it is, and then you add the constants a and b. But now since we have a polynomial here, by the way, we're done with trigonometric. Now we have a polynomial here. So when you have a polynomial, you will replace the constants, you will replace these constants by the highest order expression of the polynomial. Highest order expression of poly. What I mean is, let's say if you have so since you have t cube here, t cube, so you can write this as at cube plus bt squared plus ct plus d. Basically what we used to do before for the polynomial cases, as we discussed previously. So we will replace these constants by this. We will replace the first constant by this, and then for the second constant, we have to add new letters. So the final answer will be a c cube plus bt squared plus ct plus d, all this multiplied by cosine 3t. And then we have to put new variables for the polynomial in the place of b, because we have to maintain linear independence. We cannot have at cube. We cannot have this expression again on the second term. So what we'll do is plus at cube plus ft squared plus gt plus h. This multiplied by sine t. Last thing to check before you think this is the final answer, you compare YH with the right hand side, as we used to do in the previous examples. So you compare if you have something similar in YH and your f of x over here. So you don't have a cosine over there, but you have a sine 3t. See? Sine 3t and sine 3t. Hence, this whole YP expression will be multiplied by x. Why x? Because sine 3t is appearing like this. Sine 3t is appearing once in the homogeneous solution, and to have linear independence, we have to multiply our final answer by x. So that's it for this question. Now, similar concept here, except that this time we have exponential and we have poly. So first find the homogeneous solution. R squared minus 6r plus 9 is equals to 0. You will have R1 is equals to 3. Let me check. Yeah, so you have repeated roots here. Plus, and R2 is equals to 3. This is repeated. Hence, your YH will be C1 e power 3t plus xc2 e power 3t. Why is there an x here? Because we need to maintain linear independence. So we have to multiply the second term by x. This is the homogeneous solution. And now we need to find our YPs. So when you look at the order. You look at the order over here. We have polynomial and exponential. Polynomial appears first in the list. Like polynomial is ahead of exponential. So now this 5t power 6 can be written in terms of at power 6 plus bt power 5, and then so on. You get what I mean. Like you have to write the highest order expression for the polynomial. So it will be AT power 6 plus BT power 5 plus CT power 4 plus DT power 3 plus ET squared plus FT plus G. This is the YP for polynomial. Now, this is multiplied by exponential. And the good thing about exponential is you have to do nothing except you multiply this by the same exponential. That's it. So basically, you have the polynomial first, then exponential. You write the highest order expression for the polynomial, and then you simply multiply by the same exponential which you have over here. You have e power 3t, so you multiply the whole thing by e power 3t. Now, our final check is to check the similarity of YH and the right-hand side. So you have an e power 3t, you have an e power 3t. So basically, what we have here is appearing here twice, one here and one here. So since this is appearing twice, we multiply our whole YP by t squared, by the way, because we're dealing with t's and not x, t squared. So even the question above, it's supposed to multiply by t and not x. Even same here, I did a mistake. So basically, you will multiply this by a variable to keep linear independence. So C1 e power 3t plus C2 e power 3t. So as said before, you find the YP for a polynomial first, then you multiply the polynomial by e power 3t as it is, and then you finally check if YH and the right-hand side have something similar. Finally, our last case, and this one you need to memorize something. You have exponential and you have trigonometric. We first find our YH. So this will be r squared minus 2r plus 1 is equals to 0. R is equals to 1. R1 is equals to 1 and R2 is also equals to 1. Repeated roots for our YH will be C1 e power t plus t multiplied by C1, not C1, C2 e power 3t. This is your y of h. Y multiplied by t because we need to maintain linear independence due to the repeated solutions. Now we need to find our YP. We have trigonometric and exponential. Trigonometric, exponential, we have to do trigonometric first, then exponential. YP for the trigonometric is going to be a cosine t plus b sine t. You take the constant here as it is, basically cosine t plus sine t, and then you put a and b. And then the last thing we need to do is multiply by exponential as it is given on the right-hand side. Now, here, for some reason, if you if you think that you should check YH, the homogeneous solution and the right-hand side, it will not give you a correct answer. Only for this scenario, when you have exponential and trigonometric, there's a special case you need to consider. If we write this as e power ax cosine bx plus e power ax sine bx, so we can see that our a in this case is 1 and our b is 1. From here we can see that e power at, so a is 1, and then cosine t. So you assume that b is also 1. So that is why, since this is not similar to this one, why is this not similar? Because in this case you would have 1 plus I. 1 is the imaginary part, and b is the coefficient of the imaginary part. So here you only have the real part. You don't have the I here. So only for this scenario, when you have exponential and trigonometric, once you're done with the YP for both of them, and when you compare what you have on the right side, you compare the A and B's for the right side with what you have for the homogeneous. So here your A is 1, the real part, but your B is 0. You don't have an imaginary part for this. So since both of them are not the same, A equals to 1, A and A equals 1, but B equals to 0, B equals to 1. So we will not multiply by another variable x or t. That's it. So now, our second last concept, which is variation of parameters. You use variation of parameters when you don't have trigonometric. No, not trigonometric, by the way. If you do not have sine, cosine, polynomial, and exponential, if you don't have these four on the right-hand side, if you don't have these four on the right side, you have to use the variation of parameters. Now you would tell me, but this looks like a polynomial. But the rule is this is 1 over x. So in this kind of concept, 1 over x is not considered a polynomial. So hence you have to use the variation of parameters. Now you start off by the same way. You first find the homogeneous solution, and here it will be r squared minus 1 is equal to 0. R1 is equal to 1, and R2 is equal to negative 1. So your homogeneous solution is going to be C1 e power x plus C2 multiplied by x. No, that's my mistake. We don't have a repeated solution here. C1 e power x plus C2 e power minus x. This is your homogeneous solution. Now, how to find YP? In the context of variation of parameters, your YP is going to be U1 Y1 plus U2 Y2. This is how you find. So this will permanently be your YP for variation of parameters. I will tell you what is U1 Y1 and U2 Y2 in a second. So you have Y1 was e power x. So as you know from before, the general solution is always in C1 Y1 plus C2 Y2. So our Y1 is e power x, and our Y2 is equals to e power minus x. Now first, what we will do is we will find the Wronskian. We will first find the Wronskian. And as we did in the very beginning, our Wronskian is y1, y2, y1 prime, y2 prime. So when we do the Wronskian for this, we have an e power x here, e power minus x, and the derivative for e power x is e power x. Derivative for this is negative e power negative x. And then you find a determinant. You find a determinant of this. So you have e power x negative e power minus x minus e power x e power minus x. So this will be e power x, and so you have e power x here and e power negative x here. So assume this is 1, this is minus 1, so 1 minus 1 would be, what do you say? Like this will become negative e power 0. E will become e power negative e power 0, and then same here, x minus x will be e power 0. So you have minus 1 is equals to 2, is equals to negative 2. So this is how you find the Röntgen. And after finding the Röntgen, we need to apply this formula, this specific formula. U1 prime is equals to minus Y2 minus Y2 g of x. This is something you have to memorize over the Röntgen, and your U2 prime U2 prime is equals to Y1 g of x over Röntgen. Now, finding U1 prime and U2 prime and then integrating U1 prime and U2 prime will give us what we need over here. You need to memorize the steps, and you need to memorize these formulas. So if I want to find, why am I writing y? If you want to find U1 prime, so you have minus, so our Y2 is what? E power negative x. E power negative x. Your g of x is what you have on the right-hand side. This is your g of x. So your g of x is 1 over x. So multiplied. So negative e power negative x multiplied by 1 over x over the Röntgen, negative 2. And this becomes U1 prime becomes e power negative x over x, or over 2x. The minus and the minus cancel out. And then here, your y1 is e power x u2 prime is equals to e power x, and then the rg of x is 1 over x over the Röntgen, which is negative 2. So in this case, your u2 prime will be minus e power x over 2x. The only difference is the negative sign. The only difference between u1 prime and u2 prime is the negative sign. Now we will integrate this to find u1 and u2. So we have to integrate this. So u1 is equals to so if you want to integrate this thing, you first take out the 2, e power negative x over x, and then u2 is equals to the integral of, I have to take the 1 minus half outside, minus half e power negative x over x. This will be e power x, by the way. So e power x over x. Now, when you find the derivative, when you find the integral of this, so how to find this integral? Let's check something. Okay, so you don't have to find the integral. You don't have to find the integral. You just have to find the in this question. You don't have the you don't have to find the integral of U1 and U2. It's up to Mahmoud. I don't know. He wrote this question. So now we can write our YP in terms of this. So YP is U1 Y1 plus U2 Y2. YP is equals to U1, which is 1 over 2 integral of e power minus x over x. This whole thing multiplied by U1, which was e power x, plus U2 Y2. Our U2 is minus half integral of e power x over x. And all this multiplied by y2, which is e power minus x. That's our final answer. So just to give a quick summary, first what you do is find a homogeneous solution, and then what you do is you apply the YP formula, or U1 Y1 plus U2 Y2, and then you identify your Y1 Y2, which was e power x and e power negative x. Then you find the Wronskian. This is how you find the Wronskian, and then you apply these two formulas. And if it's possible, if it's easy and possible to integrate, then you can integrate. Otherwise, you can keep your answer as it is.